Hello everyone, this is Wolfgang and we are ready for a new Ethereum video. This time we are going to talk about the fundamentals, the basics of the protocol. I think it's always interesting as a refresher and I hope it's also useful for new people who want to look at the protocol and understand how it actually works. At least the basics. We're not going too deep here, but I think there are some important fundamentals that it's good to know for everyone who cares about Ethereum. So let's start. I will cover the basics of the protocol in 90 minutes. That's the target. So it's quite ambitious in the sense that there is a lot to talk about, but I hope I can stay in these 90 minutes. Let's see. We have 4 sections. We start with the fundamentals, then the execution layer, a consensus layer, and future development. Let's go. Fundamentals. First of all, first question. I think I'm always asking myself, it's important. You need to have a good answer to this. So why are we here? Why are we talking about this? Why do we care about Ethereum? What's the point? This is the first question, always. So why are we here? We believe, or I believe that there is a set of application user-based pairs for which decentralized trust brings added value. So big sentence here, we need to clarify a little bit some things. First of all, there is this big concept of decentralized trust. It's something special. Decentralized trust is what Ethereum is bringing. We'll talk more about it, but this is the source of everything, you see. Decentralized trust. If you have decentralized trust, then there are some pairs, like some applications and some users, or groups of users, that's why I say user base. When you put them together, then they get additional value from decentralized trust. So decentralized trust is not useful for everything. It's not the end all be all, but there are some application user-based pairs for which this actually makes sense. So there are different perspectives, different ways to look at it, or different opinions, beliefs. What is this additional value? So it's either more value, meaning that whatever you get from decentralized trust is better than what you would get without decentralized trust, so with a fully trusted alternative, like a trusted third party, or is the only way to get value. So basically, for certain applications and user base, the only way for this to work, that the application is actually useful, it must have a source of decentralized trust. That happens when you cannot trust anyone. So if in an application you cannot rely on a fully trusted third party, then you need decentralized trust because there is no alternative. So this is what we believe we can offer. There is also the possibility that actually there is a third party and you get applications based on this trusted per third party, but with the decentralized trust subset, you get more value. We'll see what this actually means. But first of all, better definition of decentralized trust. What does it mean? That you start from a certain situation or a certain application where you know there is some trusted third party, like because you are forced to trust it because there is no alternative, or that's what you believe. Well, then you identify, minimize, and remove any dependency on central authorities or single points of failure. So you have decentralized trust when there is no authority that can change the rules or that can basically modify anything in the system just by their authority or power. When you have decentralized trust, you can build decentralized applications that come in different flavors or anyway different targets. You can provide assets, services, or decentralized organization. But at the end of the day, what you have to provide is user value. So this for me, it's very, very important. Let's never forget. The end goal is not decentralization for decentralization, but providing more value to certain pairs of applications and user bases. All right, what do I mean when I say more value, better value? What is this? Like, what does the user actually want? It's not something like arcane and difficult to explain. It's very simple. It's not like the user wants something that you cannot imagine. These are the obvious things that you can imagine. So what does the user want? Independently of applications, or in most applications, you can say that user wants the application to be cheap, to be fair, or at least believe that it's fair, feeling that there is fairness, that the application is fast, so it wants responsiveness, or they want accessibility. It must always be available. Should be safe. It shouldn't, suddenly not work in ways completely unexpected or wrong. And the user most probably wants privacy. So let's not forget about that, because it's not easy to achieve in decentralized systems. In any way, this is what the user wants, and this is what I mean when I say we have to provide additional value. Now the question is, what are the pairs of applications and users for which decentralized trust is actually bringing more value, or is the only way to bring value? And then another question, but that's for another story. Is this possible? Does this make sense only in dystopic scenarios or, very bad scenarios, post-apocalyptic scenarios, and then we build a bunker coin and that's it? Or we can provide additional value also in a normal scenario like the world has today? Of course, I believe we can, and we're going there. But that's the question. Okay. So how do we achieve this additional value? With a decentralized state machine, because at the end of the day, all the effort or most of the effort in blockchain technology development at its core, if you go really at the core, what we are trying to provide is a decentralized state machine. So the question at this point is, what is a decentralized state machine? And this is a good question because we are starting to introduce some important concepts. So what is the state? When I say state, I mean a database. So I know that some people don't like this, talking about databases. It's like it's not that fancy word, but at the end of the day, it's something very important. Database means valuable information for many users, for which you want to ensure integrity. So when we say safety, we mean data integrity of the state. So for now, we're talking about decentralized state machine. What is the state? Is a database. Then, what is a state machine? It's the software enforcing protocol rules to update the database. Okay? So there is a database, the database is important to the user, and people don't want just to read and look at the database, but also do operations. Operations in a way that, with safety, like nobody can break the rules and so on. But what I want to say here, the state machine is the software that allows to update the database according to certain protocol rules. Now, that's a state machine. What is a decentralized state machine? That is what we're trying to provide thanks to decentralized trust. It becomes decentralized when you need consensus among open membership nodes, so permissionless nodes, but we're going to look more in detail what I mean, to update the database. So there is not just one authority, centralized authority that updates the database and say, trust me, I will apply the rules of the state machine. No, it's not like that. It's decentralized if the updates to the database happen after consensus among many nodes and open membership nodes. But we'll see more in detail. It's because decentralized, it's much more difficult to achieve, but this is based on decentralized trust, and again, our theory and our thesis. And that's why we're here, because otherwise it doesn't make sense. Our thesis is that decentralized trust and decentralized applications built on top provide more value, or will provide, or can provide more value, at least for certain pairs of applications and users. All right, so that's what we're trying to build. And when I'm going to talk about Ethereum, because we're getting there, trust me, I'm going to talk again about decentralized state machines and how we achieve this on Ethereum. So imagine this end goal of having a very nice decentralized global state machine synchronized at the speed of light. Let's go. So why do we want that? Why is that interesting? What does this decentralized state machine, global state machine, what does it achieve? And what does it give you? Transparent protocol rules. Very nice. The rules to update the database are clear to everyone. They're transparent. There is nothing obscure, nothing someone is hiding. You know the rules. Then there is no single authority that can just change the rules. Nobody likes that. There is this state that you care about. It's valuable information. And you like that there are clear rules on how to operate, how to change the state or request changes to the state. It would really suck if there is a single authority that can just change the rules overnight. Horrible. So that's power of decentralized trust and decentralized state machine. Nobody can just change the rules on you. Amazing. Okay, next. Yeah. So why is that interesting? Well, because this is the only way to achieve efficient social coordination at a global scale. So this is another very important concept on what we can achieve with decentralized trust. Scale social coordination. Because social coordination, humans, can coordinate efficiently up to a certain scale. And after you increase this scale, you add more people, and they are farther away from each other. You can still coordinate, but the efficiency goes down. All right. So what we're trying to imagine is a state in which we can have efficient social coordination at a really global scale. Thanks to these tools, we can have internet-native settlement and property rights with trustless data integrity, permissionless innovation, and composability in a way that it's just impossible otherwise. All right, now we talked about this global state machine, this decentralized state machine, and there is a lot of nuance. We will talk about nuance in the fourth section. But let's say we have as a goal this decentralized state machine. Now, there are many different ways to provide a decentralized state machine. I was very generic because I think it's important to have the core definition, like really go to the core of what you're trying to build. And that's the decentralized state machine. But then there are many different ways to add the features, to optimize for something or for something else. So let's look at what Ethereum wants to achieve more in particular. It's not just a decentralized state machine, but it's a general purpose decentralized state machine. So this is one first thing we need to say. In this state machine, you can do pretty much any kind of operation. Okay, well, according to the protocol rules, always, but there are, it allows you to express, it has very high expressibility, and you can basically have any kind of algorithm, any kind of software, any kind of operation on this decentralized state machine. Remember the vision of the world computer. So in that sense, Ethereum is general purpose. Other extremely important values of Ethereum for which really there shouldn't be no compromise, they are censorship resistance and credible neutrality. Censorship resistance means that any user who cares about the Ethereum state should be able to submit transactions or anyway to submit requests to change this state. We will see how it works, but the idea is that there is nobody that is just censored and access to Ethereum is prevented just because we don't like them. That shouldn't happen, all right? Then we have credible neutrality, meaning, and this is somewhat related, but maybe a little bit more generic, but anyway, what we mean here is that nobody is better than others, there is no preference on certain parties and everyone is treated in a fair way, let's say. Now, what is also important is that this neutrality is credible, like it must be obvious, it must be very clear to everyone that there is neutrality. It's not just neutrality that can be proven in theory, but then you don't really know if you don't understand some very complicated theory. This should be obvious. This is what I mean on credible neutrality. Then we need consistency, meaning that the state is safe and there is nothing weird happening against the rules, Availability, in the sense that this should always be available, this decentralized state machine. If you want to read the state, if you want to request to write the state, this should always be possible. And then another very important concept, end user verifiability. Like the user should be able to really verify all the properties here, consistency of the state, data integrity, without trusting anyone, like not even a node of Ethereum, we'll see. The user should be able to verify that everything is okay and everything is working as expected. Every user, that's really the challenge. All right, let's go. We're still in the fundamental section, but we are getting closer to the implementation, to Ethereum. So we're getting there. Let's start talking about the Ethereum network. This network is a collection of nodes. So let's see, we have here this diagram, and we start from the concept of the state. I mentioned already the state when I talked about decentralized state machine that you want to provide, because it's what, based on decentralized trust, is the first ingredient to build these decentralized applications that eventually will provide additional value, more value to certain users for certain applications. So what is the state? More concrete, more explicitly for Ethereum? Well, again, it's a very generic definition, but we need it. State is the database and it's valuable information for Ethereum users. These are all Ethereum users. You see them here in the zero section here, zero step of this cycle. These are all Ethereum users who care about the state because it's important information. So, for instance, part of the state is the balance of every Ethereum account, how much Ether is inside, or anyway, is associated to every account. That's obviously very important information, no? There is, of course, much more, but it's just to give an idea. Users care about the state. Then we have to talk about nodes and consensus participating nodes. Maybe the best way to talk about these things, introduce them, is to look at this cycle. This is the transaction life cycle. So we have the users who care about the state. Fine. But then at some point, one user, instead of just looking at the state, says, okay, I want to make an operation. I want to change something in the state. So what does the user here needs to do? They have to submit a transaction. A transaction is a request to update the state. We'll see more in detail. But that's what the user wants to do. The user wants to change the state. Okay, they have to submit a transaction to the Ethereum network. There is a collection of nodes. Okay. So how can the user submit the transaction? The user needs access to a node, so a member of the Ethereum network. And this can be their own node, or it can be connected through a wallet, trusting another node. But anyway, to send a transaction, you need a node. So what is a node? The node is hardware plus software needed, so it's a machine running an Ethereum client, needed to read and write the state. So again, the state is the information you care about. You can read, or you can request to write, to be more clear, because it's not like you just go and write whatever you want. So you request to write by sending a transaction. But anyway, the user submits the transaction because they want to update the state. For instance, they want to send Ether to someone else because they want to buy something. All right, so you need this node. This is a box with the Ethereum client running on it. You send the transaction, and suddenly the transaction is propagated to the network. So network is the collection of Ethereum nodes in their peer-to-peer network. Very nice, they talk to each other. And when the transaction is propagated, there is a subset of these nodes that not only look at the transaction and see, okay, it's a nice transaction, it works, it's valid and everything. There is a subset of these nodes that I call consensus participating nodes. And I know it's long definition, a long terminology, but I like it. So these nodes, consensus participating nodes, not only look at the transaction, but also come to an agreement on what is the next block. I'll talk about it more in detail, but what I mean here is that they put the transaction inside a block in a list of transactions, and then the transactions are executed, and the state is updated. Anyway, what are these consensus participating nodes? These are the nodes that have this power to actually decide what's the next transaction, and they ensure that the state is updated according to user requests and protocol rules. So there are many users at the same time that request to update the state. The consensus participating nodes have the role to collect the transactions and come to an agreement on which transactions are executed in which order, and then at the end the state is updated according to the rules. But let's go more in detail on some of these steps. So here I introduced the Ethereum Network. Next, we are going to introduce execution and consensus. That are also the next sections of the video. So let's start with the execution, because I have some other important, definitions to provide. Transactions, blockchain, and verification. Transactions, we talked about transactions already. The user wants to change the state, want to modify the state, they want to do something, so they submit a transaction network. We talked about it. Now, the blockchain, and I introduced the blocks. The blockchain is a data structure allowing nodes to verify the integrity of the state. And it's an append-only list of transactions. Transactions can only be added to the blockchain. Basically, this is a data structure that grows. And you can add transactions at the end, but you cannot put them randomly in the middle. We'll see more in detail how it works, but in principle, the concept is that this is append only. You can only add at the end. And you don't add the single transaction, but you add entire blocks. And blocks are lists, ordered lists of transactions. So for instance, here you have 3 transactions in a block, and you add 1 block at a time. Good. So what do I mean by verification here and the data integrity of the state, and what's the point of the blockchain? The point of the blockchain is that if you download the blockchain, let's say you're a new node, you download the state, you download the blockchain, and basically you don't have to trust anyone on the state that you received, because when you re-execute the whole blockchain, meaning all the transactions starting from 0, at the end you will get the state. So you will get the same state as everyone else. This is the power, basically, of the blockchain. It ensures the data integrity of the state. You know that this is the right database, because after re-executing all the transactions, you get exactly that. And you know that the blockchain is a data structure that works such that this is append only. You cannot modify the history. So you execute all the transactions and you get the state, and you're happy because you can verify that there are no differences and the state is the right state of the blockchain. Cool. Then consensus. We touched on this a little bit, but let's go more in detail. What is consensus, to be precise? It's a method to find an agreement on transaction ordering in the blockchain. So again, imagine there are many users who are sending transactions at the same time. And you have to decide, or anyway, there must be a method to decide which transaction is executed first. And it's not obvious, because, if there was only one node, maybe you can say, okay, let's order them in the order they arrive to the single node. But it's not that simple when you have many nodes and you don't know exactly who you can trust and which not. They have to come to an agreement. So this is what consensus is a method to decide the order of the transactions, or more precisely, the order of the blocks in the case of Ethereum. You don't order the single transaction, but blocks of transactions. Then other important concepts for consensus are block proposer and fork choice. So as I said, you send the transaction to the network, and there is a subset of these nodes that are consensus participating nodes. Now, one of these consensus participating nodes, for a certain time, will also be elected as the block proposer. So there is only one of these consensus participating nodes that is selected to propose the next block. We pick one of these consensus participating nodes and we say, it's your job. For this amount of time, you receive the transactions and you decide how to order them. That's the block proposer. The block proposer makes an order, puts them in a block. The block is published to the rest of the network, and the rest of the consensus participating nodes looks at this block and applies a so-called fork choice rule. We will see more in detail. But what I mean, they apply consensus rules to decide if it becomes part of the blockchain, the next block. So that's to introduce consensus and the consensus layer. We'll see more in detail how it works in the third section of the talk. But first, execution layer. So let's go. For the execution layer, very important concept, again, the state. So let's talk about the state. And finally it's becoming more concrete and close to Ethereum. It started from very generic concept because I think it's important to have the definitions down that are as generic as possible, because then you can apply them also to other systems. And it's important to know the basics. Anyway, so what is this valuable information for the Ethereum users? You have all these Ethereum users looking at the state. Why? What is inside the state? And in the case of Ethereum, and to be precise, I'm talking about the execution state here. But anyway, the word state, this is a list of accounts and associated data. This data can be Ethereum balance, Ether balance, so Ether, the asset, then code and storage. This is data that can be associated to accounts. So you see we have different fields like the address to identify the account, the balance in Ether, the code, the storage, and anons. Now, so we have the state. It's really just a list of accounts with their data, and for the data, there is something that is very easy to understand. It's clear to everyone who ever used Ethereum. There is some Ether balance. But then you can have more, like code and storage. This is the state. Then, what are the state machine operations? Like, what can you actually do on this state? Because remember, I said, at some point, a user wants to do something. It looks at the state, at some point, it requests a write. So it sends a transaction, because it wants to change the state. So it wants to execute the state machine operation. What are these operations that the user can do? Different kinds. So transferring ETH, for instance. That's something you might like to do. Depends. Something you might like to do. Send Ether. Maybe you want to sell anything. Anyway, you transfer Ether to another account. You can do that. That's a very simple state machine operation. You move Ether from an account, your account, to another account. But then, because remember I said this is a general purpose state machine, there's some other very important things that make it clear that it's a general purpose. You can deploy code, like very generic, anything, any kind of code. You deploy it, and it's there on Ethereum, on an account. You put it in an account. And the other thing you can do, execute code. As I said, accounts can have code. So you know some account with some code, and you like it in the sense that you want to execute it because it would change the state in a way that basically it's useful for your needs. So you call the account and you execute the code stored in the account. You can see that with these three simple operations, I'm saying that you can do pretty much anything. And that's why it's a world computer, general purpose, decentralized state machine, and so on. That being said, there is one important detail that is good to know. There are two types of accounts. There are contracts and so-called EOAs, or externally owned accounts. So the contract account is the type of account that has indeed all the fields that I have discussed. And contract is a program, okay? It's like software, or anyway, it's related to code. I'm talking about code. So smart contracts, contract accounts, these are programs. And in this case, you have all the fields I discussed. So in the contract, you will have code and storage with the data related to the code or modified by the code, for instance. But then you have this other kind of account that is the EOA, externally owned account. And this is the typical account that you make for yourself when you are onboarded to Ethereum. You will have an account with some Ether, right? So that's an EOA account. And what is particular about externally owned accounts is that they don't have code, they don't have storage. These accounts are simply controlled by keys. So private key. And ultimately by users. So the users will have their keys, and those keys will allow them to control externally owned accounts. The other accounts with all the fields here, they're controlled by code. So that's a way to look at it. Contract accounts are controlled by code. EOAs are controlled by keys, users. Okay, so we talked about state. We talked about state machine operations. Now I'm talking about something very related to the operation. It's more like the outcome of the operation. It's a state transition. It's an important concept to think about. So let's look again at the transaction, but now more specifically transaction in the context of Ethereum. What is a transaction? It's a data package, data formatted in a certain way that is understood by Ethereum, etc. It's data package signed by an EOA, externally owned account, the one controlled by keys, that's by you, the user, that is describing a state machine operation. So the transaction is some data that says, I want to change this. I want to do this. I want to do this operation on the state, on the database. Now, what is a state transition is the outcome of the transaction. So you have a state at time I, let's say, or anyway, you have a state at a certain point. If you apply a transaction, you go to a state I+1, because the transaction is a way to change something in the state, right? Because that's what you want as a user. I want to change something, of course, according to the rules and so on. So when you apply a transaction through a state transition function, you go from state I to state I+1. How does that work? That works thanks to the Ethereum virtual machine, the EVM. So this EVM is a general purpose, again, because it can do pretty much anything, virtual machine that is implementing the state transition function. And this, it's a state transition function is telling you all the rules to go from one state to another state when you apply a transaction. So, that's what a state transition is. Now, a few more words on transactions, like how the transactions actually look like, what are the things that you can do and define in a transaction, because up to now I just said it's a data package that is signed by an EOA. Actually, this is important, like only EOAs can initiate transactions. So only keys controlled by users and not contracts independently waking up to sign transaction. No, that's not happening. This must come from an EOA. Okay, so what is inside the transaction? I just said it's a data package signed by an EOA that describes a state machine operation, right? That's all true. But now, what is actually inside this data package, and what are the contents of a transaction? There are different fields that are important to discuss. So there is from and to, like source address, target address. The source address is the initiator of this transaction. So remember, the user who is sending the transaction to the network, they will need to sign to provide a proof that they actually control the keys that are related to that account. So they will also add a signature. But anyway, there is this source address, is the initiator, the user. Then there is a target address. So for instance, a transaction might be something as simple as sending Ether. Okay, but to whom? So that's the to field. Then you have a value, that is the Ether amount. You want to send Ether. Okay, how much Ether? So you need value. Then, and here we move to the more general purpose side of the state machine. There will be some input data. And then we'll see more in detail what can be in this input data. The last field I want to mention, this is a collection of fields. This is information on transaction fees. So these are fields that you can fill to give information on the fees that you will pay. This will look more in detail, but it's important to know it's there. So now the question is, what is this input data? This depends on the kind of transaction. There are different transaction types, and there is a very easy way to classify them. the transaction type is different according to the kind of account that is in the target address. So we have from address and to address, source and destination. And in from, you always have EOA. Because as we said, only EOAs can initiate transactions. Fine, easy. But now, the target of the transaction defines the transaction type. Because an EOA can send a transaction putting as a target address another EOA or a contract, and then the transaction type is different. So if it's to another EOA, remember the EOAs don't have code, don't have storage. All you do with the transaction from an EOA to an EOA is transferring it. And, it's a very important transaction, so it's okay. You're sending Ether to another EOA. Then, what if you put 0 to the target address? So there is no target. That is what you do if you want to deploy code. As we said, there are 3 different state machine operations: transferring Ether, deploying code, and executing code. So here we are in the deploying code part. You don't put a target address, but you put some input data. And what is this input data? Is the code of the contract. You want to create a contract. You want to deploy code. You want to create a contract account. So you write your code, you put it in the input data, and you send this transaction from your deployer EOA address to 0. And then the contract is created, and anyone can execute it. Amazing. So that's what you do. You put it here in the input data. Then we have this other transaction from EOA to smart contract or to a contract account. This is the third state machine operation that we mentioned, where you not deploy, but you actually execute the code. So you execute a contract, this contract, the one you are sending the transaction to, according to data. So in the input data here, you will put some important information for the execution of the code. We'll see more in detail. But what this is, you say, I want to execute this specific part of the code according to specific parameters. So we'll see it. But yes, in the data, you put important information for the execution of the code. Yeah, and we're seeing it here. We are talking now about the contracts. So this, to give you an idea of how contracts look like, or, well, this is the Solidity language to, the EVM is not executing this, but it's executing bytecode. So this is the programming language, then it's compiled, and it's basically compiled in a form that is that can be read by the EVM bytecode. Anyway, for all intents and purposes, you can say this is the code that you want to execute. As a user, you care about this, and you want to execute certain functions in the contract. So the code that can be deployed and executed on Ethereum is written in Turing-complete languages, meaning that you can define pretty much whatever function, and these are Solidity or Viper. And then the language, in this case we have Solidity, and then it's compiled in EVM bytecode. Now, some important things that we need to mention. This is a general purpose. So you can do anything. It can work with permanent storage or more volatile memory. Permanent storage is more expensive. We'll see the fees, how it works, but it's intuitive. If it's permanent, it takes more resources from Ethereum, so it's more expensive. Or volatile memory. And other things that are important to know is, what is this data? As I said, there is this transaction to execute code, and in the transaction field, you will have input data. So what is this data? In this data, you will put which function exactly you want to call in this code, and which parameters you want to provide to submit to the code. Why? Because, let's look a little bit at the code, at this example of a code. And this is a very, very simple contract. It's a wrapped Ether. So this contract allows you to send Ether to the contract and get in return this token that is wrapped Ether. And this is useful for composability in DeFi interaction. Make Ether an ERC20 token, because there are other applications that require ERC20 tokens. Good. So let's see. There are some important things that I want to highlight here. This is the storage. And basically you have a map of all the balance in wrapped Ether that is owned by every user. So a user comes and deposits Ether because it will not only provide input data but also Ether, in the value you put Ether, and then the contract takes care of keeping track of which user deposited which amount of Ether, and so it got wrapped Ether in return. You have to keep track of it. And this is in storage. And, when we have looked at the accounts fields, there is code, but there is also storage. It's a very important field in the account. So it's defined this way. Then you have different functions. I didn't put them all, but you have a function to deposit and a function to withdraw. Here in the code, you can see the name of the function, deposit, or here, withdraw. And so if you want to deposit Ether in the contract, in the input data, you will call this function, this deposit. In this case, there are no parameters, so you only need to provide this, let's say, to the contract. I want to execute deposit function. And since you want to deposit, you have to also provide some Ether, of course. So this function, what does it do? As a user, you deposit Ether and you receive wrapped Ether one-to-one. Then the next, the first instruction is updating the storage. So we have seen here mapping for storage, and you have this balance of variable, and this is Ether deposit by each address. So what do? You update this mapping, this storage, at the end of the day, this database, and you keep track of the deposit. So you keep track of the fact that the sender of the transaction has deposited this value of Ether. And that's pretty much it. That's the function. You are really just updating the storage of the contract. The contract stores and keeps track of how much Ether was deposited by which address. That's it. Very simple function. Then you have another function that is here to withdraw when you want to give back wrapped Ether and receive Ether that you originally deposited. So you unwrap Ether, you get it back. And in this case, you have to provide a parameter. So that's why I said before, when in the input data, you don't provide only the function, but also you might need to provide parameters. And in this case, the parameter is how much Ether you want to withdraw. For the deposit, you didn't need to provide a parameter because you just provide Ether, you send it. It's in the value field. Here you have to say how much Ether you want back, and then you have to provide this parameter, goes into input data. And this works quite like in the inverse. First of all, you check the storage, like, did you actually deposit Ether before? Do you have enough in this storage? And if yes, then the storage is updated. And this updating the storage is actually the fact that you are giving back wrapped Ether. That's all it is. And at some point, you have an actual transfer of Ether, so you get it back. All right, now for another extremely important concept for the execution layer is gas and transaction fees. Let's talk about the concept of transaction fees and gas first. So executing transactions requires time and resources, like the nodes. Remember, there is this user that sends the transaction. The transaction is propagated to all nodes, not only consensus participating nodes, all nodes. And the nodes can look at the transaction, execute it, validate it, and most importantly, the consensus participating nodes will need to decide if this transaction is going into a block that is actually appended to the blockchain and becomes forever history of Ethereum, ensuring the integrity of the state. So this is an important operation, and you need to do it to get to consensus on what is the blockchain. But to do that, you are requiring time and resources. Like these nodes are actually machines that are running software and they have electricity costs, and it cannot be for free. Also because, if you want to attack the network and it's for free, you can just spam the network with transactions and ask all the nodes and the consensus participating nodes to execute them for free. They get overloaded, it doesn't work. So you need to find a way to meter this requirement, this consumption of resources. How do you do that? With the unit of resource consumption, and that's gas. Gas is just a way to measure or to quantify resource consumption. Because then you can ask transaction fees according to how much is consumed in terms of resources. So to meter and to quantify, you use gas. And there are two kinds of resources in Ethereum. So we have two kinds of gas to track these two different resources. There is execution gas and data availability gas. So execution gas, we can just say also just gas, because some time ago there was only one resource, there was only execution gas, so we only had gas. But now we also have data availability gas, so I make this differentiation here. Data availability gas is also known as blob gas or just blobs, honestly. So we have gas, unit of resource consumption, and then the concept of gas metering, that you measure how much gas is consumed by different transactions. Thanks to the fact that you can have gas metering, you prevent spam, and you can charge the user the use of network resources. So if a user needs network resources, if a user consumes network resources, then we will charge a fair amount of fees, transaction fees, according to the gas linked to a certain transaction. So different transactions will have different amount of gas consumed, and from there you calculate the transaction fees that must be paid by the user. Right. So a transaction, at the end of the day, is described, or anyway, produces a list of EVM operations. It needs a certain amount and type of EVM operations that describe the state transition, or that are needed to get the state transition that is wanted by the user. So there are different types of EVM operations, and different EVM operations cost a different amount of gas. There are certain operations that are light in terms of resource requirements, and others that are heavier. So different operations cost a different amount of gas. And each transaction has a different gas usage based on the required EVM operations. Yeah. Now, another important concept to know about gas is gas limit. So remember, I said blocks have a certain amount of transactions inside, because we are ordering blocks and not transactions. We put a list of transactions inside the block. Now the question is, how many transactions can a block proposer put inside the block? Not an infinite amount. There is a limit. How do you calculate the limit? Thanks to gas. So again, we make sure that we are not consuming too much resources, or that we are not asking the network to do too much work, thanks to certain limits, setting certain limits. So inside a block, you can have as many transactions as long as they don't pass altogether a limit of 30 million execution gas and 6 blobs. You cannot have more than this, you cannot have more than this. These are the two resources. And if there are even more transactions, there are more users who still want to enter in the block, well, some of them will need to wait. You cannot pass this limit. That's the absolute maximum, 30 million gas, 6 blobs. So what will happen to the pending transactions? Well, they need to wait. There is more space in the next block. So that's how it works. We talked about the concept of gas, and we anticipated that, thanks to this metering, then you can actually quantify the transaction fees. There is an amount of Ether that must be paid by the user to have the transaction executed. Now, we said that for the transaction, you can calculate how much gas you need to pay, because the transaction is translated into a list of operations EVM operations, opcodes. These operations have a certain amount of gas linked to them. So you sum all the gas according to this list, and you have the total amount of gas, and you say you have to pay this cost of gas, this gas. But what is the cost of gas? It's not like 1 unit of gas is equal to a certain amount of ether and it's fixed. This is dynamic. And that's why we talk here about fee market. The cost of gas changes. It's dynamic. And is depending on the level of congestion of the network. What do I mean by this? I mean that if the network is more busy, like there is a lot of activity, a lot of users who wants to operate on Ethereum, then the cost of gas will go up. Because there is a lot of requests. There is a lot of competition to get in the block because there are many users that really care about updating the state, And you have to find a way to prioritize certain users than others, or anyway, you need to keep you don't want this to explode, basically. You need to charge the right fees. Supply and demand. So the higher the demand for Ethereum resources, the higher the gas cost. How does this actually work? We talked about a gas limit, like you cannot put more than 30 million gas in a block and more than 6 blobs in a block. But there is also this other parameter, that is the gas target. So the fee market and the update of the cost of gas changes depending on whether there is more demand for Ethereum resources than this target or less demand. Basically, the idea is that at equilibrium, we want to have, like on average, we want the blocks to be filled with 15 million gas, like execution gas, and 3 blobs for DA. This is the average that we want to target because we know that if the blocks have this kind of resource consumption level, then the network is in a healthy state, meaning that all the nodes can keep up. We are not asking too much to the nodes of Ethereum. So this is the target that we want to achieve. Now, what if there are spikes of demand? Like suddenly there is a lot, many users who want to be in the block at the same time. You will fill the block more than 15 million gas. Like you can go up to 30 million. If you do that, then the next block, the cost of gas will increase. The opposite, if there is no demand, like a low demand, then the block, you will not be able to fill it up to 15 million. And then you can start decreasing the cost of gas. So this is how it works. You check the target. And if the blocks are filled above the target, then the resource cost increases, otherwise it decreases. Now, as I said, there are 2 kinds of resources. There is execution gas and DA gas or blobs. And for this to make sense, you want to price them independently. Or anyway, it's very nice that they're priced independently. So the cost of execution gas depends on how much execution gas is in the block. The cost of DA gas depends on how many blobs you put in a block. And just to give an idea of some of the numbers, let's say that you completely fill a block with 30 million gas, then the next block, the cost of gas, the base cost of gas, this base fee, will increase by 12.5%. Okay, then, now that we have all the ingredients of the concept of gas and the fee market, we can talk about the transaction fees. So how much ether you actually need to pay to operate on Ethereum, to have this transaction executed. You have 2 components. You have the base fee and the priority fee. And the transaction fee, at the end of the day, so ether that you have to spend, will be the amount of gas that you need, and this depends on the transaction that you're sending, multiplied by the base fee plus the priority fee. So there are 2 components. The base fee is what we talked about in the previous slides, and is automatically calculated by the protocol. This is the cost of gas calculated by the protocol in Ether. and is changing according to the level of congestion of the network. So more demand, higher base fee. Low demand, the base fee goes down. This sets a floor price on transaction because the base fee must be there. It's calculated by the protocol. There is no way around that. So that's the floor price. Now on top of that, you can add the priority fee. You as a user, when you send a transaction, you remember there was that field with the fee data. You can add the priority fee. That's up to you. And you can do that to incentivize block proposers to include the transaction. The block proposer is that one consensus participating node that is selected for a certain amount of time, of course, not forever, to decide what is the next block. Deciding what is the next block means deciding which transactions are inside the block and in what order. Now, you want your transaction, you want to make very sure, like you really want your transaction to be in this block. One thing you can do in periods of very high congestion. Anyway, one thing you can do to incentivize block proposers to add your transaction to the block is to add a priority fee. So that's on top of the base fee that is calculated by the protocol depending on the demand for the network. There is another very important thing to know about these two components, that the base fee is the floor price times the gas used. This part of the transaction fee is burned. So the ether that you spend for the transaction fee, a part of it is just burned, disappears, doesn't exist anymore. The other part, depending on the priority fee, is instead going to the proposer. I mean, that's why it's an incentive. They're incentivized because they get it. They get the priority fee. So that's where the ether is going. A part of that ether is going. Cool. Then I think this is the last slide for the execution layer. Let's talk about blocks a little bit more in detail. I think I said this before. The block proposer and anyway consensus is not about ordering single transactions, but about ordering blocks of transactions. So in a block, we have an ordered list of transactions, like here from TX1 to TXN. And this is the state transition. Again, more accurately, you go from state Y to state I plus 1, applying the state transition function, not to a single transaction, but to batches of transactions. So you go from this state to this other state after you apply all the transaction in the block. It's a batch execution of transactions. So this is what is inside the block. Like not everything, but it's a selection of the fields inside the block. So for sure, you're going to have the list of transactions. But then you have also other important fields like the state root. This is a hash of the whole state, like it represents the state of Ethereum, or more precisely, the execution state. This is what I was showing with all the users looking at the state, the world state. That's the information that they care about. In the block, you don't put all the storage. The state is stored somewhere else. It's a database. But here you put a commitment to the state. And then there is other important information like the base fee per gas. This is the cost of gas. Is how much gas has been used for this block by all these transactions. It's information that you need because then for the next block you will need to know what is the next cost of gas and so on. So this is an execution payload, and this is what we talked about until now, the execution layer, the EVM, how to change the state. You send transactions, you create code, you deploy code, you go from one state to the next state. That's the execution part. Now in a block, you don't have only the execution payload, but you also have information important for consensus. And that's what we're going to look at in the next section of the talk, the video. Consensus layer. So what do we have here? Well, we have a link to the previous block. That's why you have a blockchain. They're literally linked, like you say, what is the previous block? But then you have a slot. I'm going to talk about this, saying what is the time at which, we will see how it works. This is the block corresponding to this specific slot in the Ethereum time, arrow time. We'll see. And then you have these attestations. And this is a very important concept for consensus. So we'll talk about this in detail. We'll see now what are these attestations. Let's go. Consensus. Okay, Ethereum consensus. I'm putting back here this slide that we've seen at the beginning on fundamentals, introducing execution layer, consensus layer. We are now at the consensus stage. And let's remind the concept. Consensus is about ordering transactions, or more precisely, ordering blocks, lists of transactions. You have these nodes. The consensus participating nodes is a subset of all the nodes part of the network that receive the transactions, and they have a method, this consensus, to decide how the transactions are put together in a block, what is the next block to be added to the blockchain. As I said, it's an append-only list of transactions or blocks. You cannot modify the history. And that's the very nice property that allows you to have data integrity for the state. So we arrive to the point of how do these nodes actually agree on what is the next block? How? With voting, with attestations. The attestations are the votes that we put in the block. It's in the block you have this history, or anyway you track who voted for what. How? With attestations. So Ethereum consensus relies on voting. That's how it works. The consensus participating nodes, this subset of nodes in the network that have this power to come to agreement on what is next block. How do they agree? They vote. That's it. They vote on their view of the canonical blockchain. I mean, on their view of what is the blockchain. Which is the right blockchain. They vote. They might have different opinions. They might be wrong. They might be malicious, whatever. How do we come to an agreement? We vote. Okay? So, relies on voting, and another important concept to know is that the block proposer, like, who decides who is the block proposer? Because remember, I said, here you have the whole network. The whole network is looking at the transaction. Then you have a subset of nodes that are the consensus participating nodes that actually do the consensus. But then there is an even more special node. There is the block proposer. The block proposer is the one node that for a certain amount of time proposes a block and says, hey people, this is the next block. And then everyone is voting. But how do you decide who's this block proposer? Random. Okay? So block proposer is randomly selected among all the consensus participating nodes. And it will make sense. It makes sense. And you can already see why it makes sense. If you remember, the values are neutrality, fairness. It's not like there is one node, one consensus participating node that is better than the others. You select randomly. Okay? But we'll see how it actually works more in detail. But for now, it's very important to know. This is random. Okay, so, well, yeah, as I said, yeah, you just vote. I mean, it's not that easy. Not that easy. Why? Because Ethereum has open participation. Like, there is no gatekeeping, there is no, like, restriction. I say, no, you cannot enter. In principle, anyone can participate to consensus. Anyone can join the network. But if you do that, if you allow such a thing, then there are challenges and issues that can happen. First, there might be too many nodes. If anyone can enter, anyone can join the network, then you might have 1,000 nodes, 1 million nodes, tens of millions of nodes. And, it's easy to say, just vote. But, it takes time to agree on who voted what is the majority, aggregating all the information. Remember, I said this is a state machine, ideally synchronized at the speed of light. And, so you want to be fast, maybe not speed of light, whatever, it's a concept, but you want to be fast. And if you're having too many nodes, it might be difficult to find an agreement via voting. And by difficult, I don't mean conceptually. I mean, it takes time and effort, and most importantly, time. So you don't want to have too many nodes. Another concept, on the other side, you might not have enough nodes. What if you don't have enough nodes? What if nobody wants to participate, So in that case, you just don't have decentralized trust because you have maybe one node or two or three. How much is enough? Big question. But if you have one node, two nodes, you don't really have decentralized trust in the way that you want to achieve. And that's the whole thesis. Like why we're here, why I'm making this video, why you're listening. We believe that decentralized trust is important. All right. So you must have a certain amount of nodes. Other challenge, if participation is open, and really anyone can join, you might arrive in a situation where you have too many bad nodes. Bad can mean faulty, can mean malicious. Like they just want to attack the network. You have to be ready for that. So that's the challenge, too many bad nodes. And if you have too many bad nodes, what's the point of voting? Like it will just not work. You cannot find an agreement because there are these nodes that destroy everything and makes everything messy. It's not working. Can't defend from attacks. So how do you take care of these challenges? Or how does Ethereum care? Well, three concepts we need to talk about. One is Sybil resistance. So I said open participation. I said fairness. I said accessibility, neutrality. I mean, it's all true. But still, you cannot just have completely open participation because then attackers or entities that want to control the network, they can just spin up as many nodes as they want because it's open and control the network. They create 1 million Sybils, 1 million fake accounts in the sense that they're all controlled by the same entity. They're Sybils. And then suddenly you arrive and you have 1 million votes. And then, again, what's the point of voting if anyone can get infinite votes just by deploying more Sybils? It wouldn't work, right? So that's why you have Sybil resistance. And to vote, and this means to become a consensus participating node, you need to lock 32 Ether. So here we are looking at another utility of the Ether token. Like, why do we need a token? What's the point? So we talked about transaction fees first. It's a way to allocate scarce resources. Ether is needed. Another important thing here, Sybil resistance. So you ask nodes to lock 32 Ether to get one vote. In this way, you take care both of the too many nodes condition, like there is an actual theoretical cap because there is a certain supply of Ether on how many nodes you can have. So you cannot spin up infinite nodes because there is this limit. You need 30 Ether. And also you cannot have too many bad nodes. It's related. So if you're an attacker, you cannot get extra votes for free. But at the very least, you need to lock 32 Ether for each vote. Next, other concept, incentives. So you have incentives defined by the protocol such that good behavior is rewarded. And what is good behavior? I mean, you're not asking much, just follow the protocol rules. That's it. Like, if you follow the protocol rules, it honestly just means execute the client, your behavior will be rewarded. So these are economic incentives, and the Ether again plays a role here, and this allows you to take care of this challenge of not having enough nodes. Because if you don't have enough nodes, you don't have decentralized trust, and then why are we here? But with incentives, with fact that good behavior is rewarded, you incentivize people, entities, to run nodes. So you will have a certain amount of nodes, thanks to these incentives. And then we have the concept of penalties, like the opposite. If good behavior is rewarded, bad behavior is penalized. And this takes care of the too many bad nodes. Like, you can't have too many bad nodes, not only because of Sybil resistance, so there is an actual limit and cost, but also because bad behavior is penalized. You will have a cost by trying to attack. And you see more in detail how it works. But that's the idea. And of course, defining the right incentives and the right penalties to have a good balance on how to take care of these challenges, it's a big part of the questions in the design of Ethereum. There's a lot of work on that, and it's continuous work. Good. Now, there is a concept that I want to make very, very clear now. You know, it's a little bit breaking a little bit the story, but let's make it super clear. Let's make a distinction between Ethereum nodes and validators. So until now, I only talked about nodes. The nodes are part of the network, and the node is hardware plus software needed to read and write the state. Anyway, request writings of the state. So, today we have a certain amount of nodes, depending on how it's measured, if it's synced, or, order of magnitude 10,000 nodes. And these are the actual machines, the boxes that are running the client of Ethereum, the software. And until now, I only talked about consensus participating nodes. I say nodes get one vote if they lock 32 Ether. That's true. But now it's very important to talk about the concept of validators. Now, you can have one node, you control it, you have at home your box, you run the client, you lock 32 Ether, you get one validator and one vote. Now, of course, nobody is stopping you from locking 32 Ether more, and you basically deploy another validator. Every validator has one vote. So one validator, one vote. But one node can control many validators. Now, it's still very important to talk about and to keep track of how many validators are there in the network, because the agent in consensus is the validator, is not the node. So a node can control 10 validators, and all these 10 validators, they all participate in consensus. So there will be 10 votes. This is important because when you talk about scaling and computational resources and time needed to reach consensus, you don't look at how many nodes there are there, but how many validators are there. Because every validator is this entity, this agent or actor in consensus that is sending messages to vote. More validators, more votes, more load to the network, more computationally expensive or anyway time resource expensive to achieve consensus. So that's very important. And it also makes very clear is that it's not like you have one node, you have one vote. If you have more Ether, you can get more votes. Also, when I said block proposer selected randomly, yes, but the validator is selected randomly, not the node. So if you control 100 validators, then you are more likely to be selected randomly as a block proposer than me, that I might have only one validator. All right? Cool. Then we can move, going back to the Ethereum approach. So we talked about challenges in consensus, not enough nodes, too many nodes, too many bad nodes. We talked about the basics of how Ethereum takes care of this. Sybil resistance, there must be some Sybil resistance. It's 32 Ether per vote. Economic incentives and economic penalties. Now, there is more that Ethereum is doing. Of course, there is much more. Anyway, there is more. And there are other properties that basically Ethereum has that make the consensus problem approachable. Because again, consensus in distributed systems with open participation, very difficult. So Ethereum has some properties that make the problem easier. So what are these properties? First, talk about consolidation. So what do I mean by this? Is that the validators don't agree and vote on single transaction ordering, so they don't vote at the level of transaction ordering inside the block, but on the ordering of the blocks. So the unit for which validators agree on the order is the block. They don't look at what is inside the block. They don't look at the order of the transactions inside the block. They just look at the order of the blocks, because otherwise it would be too much. Imagine if all the validators had to vote on every single transaction and say, yes, this is the next transaction. No. The block proposer proposes a block, and then the validators decide, yes, this is the next block, and the previous block was this block, so they agree on this order. Consolidation. Other point, time synchrony. We can only have a new block every 12 seconds. So we have a concept of time and synchrony. This makes things easier, because validators know when a block is supposed to arrive. Everything is regular, every 12 seconds. It's not random, because to that so much complexity, this helps. Time synchrony. Then, proposer monopoly. What do I mean by this? Is that, as I said, there is a proposer, they selected randomly, not a node, a validator. Now we're more precise. One of the validators is selected by random. Now, for 12 seconds, this validator will have total monopoly, full control for 12 seconds on what is the order of transactions in the block. It's only up to proposer for these 12 seconds to provide this block to the rest of the network and say, people, this is the next block. And I decided, like everybody knows, because that's the rule, I decided which transactions are inside and in what order. As you know, a proposer might decide that they don't want to add some transaction. Anyway, this is of course, the proposers are always incentivized to add transactions because there are priority fees, and the priority fees go to the block proposers. But yeah, so monopoly. And why are we doing this? Because it makes consensus easier, and consensus is super difficult. So it's okay. I mean, yeah, there is this. Now, I'm not saying it's impossible not to do this. There are attempts to have concurrent proposers and so on, but this makes things easier. You don't have many proposers at the same time, but every 12 seconds, next proposer selected randomly, full monopoly. And then the last point, I say here, the fork choice rule is deterministic. This is what I'm trying to say here. What I actually want to say here is that the process of voting, it's actually very easy, or anyway, it's deterministic. You are not asking nodes to have some subjective interpretation of, of what is the next block. All the nodes, in principle, are running the same software that is really just applying a deterministic algorithm based on what they see to decide what is the right order of the block, or more, in other words, to decide if the block proposer is right. Let's put it this way. So all the nodes vote, all the other nodes, because one proposer is proposing the block, all the other nodes vote on what they believe to be the right chain according to a deterministic algorithm. So this helps. There is a rule. You are asked to vote, but voting means just apply the rule. That's it. So that makes things easier for coordination. Okay, so let's talk about time in Ethereum. There is a time synchrony, so we already touched on this. We already mentioned the slots. This is a part of the block, a field in every block. In the consensus part of the block, it's written the slot number. So what is slot number? What is a slot? It's a unit of time. time in Ethereum, starting from the genesis, like the first block, the start of the Ethereum network, it's divided in slots. So you have one slot from 0 to 12 seconds, then another slot from 12 seconds to 24 seconds, and so on, forever. Divided in slots, regularly, easy. Now, what if we zoom out? We zoom in. We zoom in on a specific slot. We see that there are internal deadlines, or I say subslots is probably wrong, not a good term. I call them subslots. Anyway, there is an internal division of time inside a slot. 4 seconds, 8 seconds, 12 seconds. So at the beginning of a slot, you have a so-called proposal deadline, and this is where you, as a block proposer, because you are selected randomly as a block proposer, one of your validators, at time 0 inside a slot, you are supposed to send the block. You have to send it soon, because you want to make sure that everybody in the network looks at the block. Because you are proposing the block, the other nodes will look at the block and will vote. So they need to know that there is this new block. And for them to know, you have to send it in advance, or anyway at a specific time, so that everyone is synchronized and everything works smoothly. Send the block at the beginning of the slot. You need some time, and this is why we have different deadlines, for the block to propagate to the rest of the network. Now at 4 seconds inside the slot, you have this attestation deadline. And this is the time, your deadline for you as a validator, so a consensus participating nodes, to vote on what is the right chain. You are going to say with your vote, this is what I believe the blockchain to be at this point. And everybody is voting thanks to these attestations, and basically the majority will decide what is the right chain. So, to keep everything synchronized and done properly, you have this deadline at 4 seconds. These 4 seconds are enough for the block proposed by the block proposer to go everywhere in the network. So everyone had the chance to look at it and update their view of the blockchain, and they can vote at 4 seconds. Now, when they vote, all these votes are messages that have to be propagated to the rest of the network. Because, you vote, but then the other people needs to know, like all the other nodes need to know what you voted, what was your vote. So this attestation is, again, propagating in the network. You need more time. And now, it's more clear what I was saying, that you cannot have too many nodes. Because if you have millions and millions of attestations, if you have too many attestations, then you will need more time for aggregation, because then you have to put together all the votes. And this concept is called aggregation. So you need more time also for the aggregation, and you have a specific deadline at 8 seconds inside the slot. So 3 sub-phases inside the slot. Now, we talked about slots. To talk about time in Ethereum, we also need to know about epochs. So that's another unit of time, and it's a longer unit of time. One epoch is made of 32 slots. We said one slot is 12 seconds, so one epoch, for instance, from slot 0 to slot 31 is 6.4 minutes. Epoch 0, 6.4 minutes, then another epoch, another 6.4 minutes, you get to 12.8, and so on. Every epoch is made of 32 slots. Now, as I said, we vote every slot. Why do you need epochs? Because basically aggregating votes takes time and resources. Ethereum wants to have many validators, okay? Ideally, many nodes, many consensus participating nodes. I mean, that's the point. But many nodes also means many validators. So we want to be able to take care, to consider and aggregate the votes of many, many validators. If you have too many validators and like if you want to have a huge amount of validators and you want to ask them to vote, all of them voting every slot, then you probably have too many validators. In the sense that it takes too much time. Unless you ask the validators or the entities running the validators to upgrade hardware requirements, and then it becomes more difficult to run a node, and so you don't have as many nodes, you're not decentralized enough, and so on and so forth. The point is that we have many validators and we are designing Ethereum in a way that we know that we want to have many validators. So instead of asking them to vote all of them at every slot, the requirement is that every validator will have the chance to vote once in an epoch, not in a slot, not in every slot, but once per epoch. One epoch is made of 32 slots. Why? Because we are dividing all the validators in 32 groups. And every group will vote on a specific slot. All this is assigned randomly in advance and rotated. But yes, they're divided in 32 groups. So you have one group that is 1 divided by 32, the total number of validators. And this group of validators votes only during this amount of time, this 12 seconds, this slot. Then you have another slot and you have another group of other 1 divided by 32 number of validators. So what is the point of epoch? The point of epochs is that by the end of the epochs, you had 32 slots, and you know that during this epoch, every validator voted once. And this means that it's a good time to take important decisions. Basically, this is what it means. Because you want to make sure, before taking important decisions, we will see what it is, you want to make sure that everyone had the chance to vote. Because, again, we are in an environment that is potentially hostile, like there are malicious or bad nodes. So you want to make sure that everyone had the chance to vote because you know that you have an honest majority. At least that's the assumption. But to take advantage of this honest majority, you want to ensure that all the validators had the chance to vote. And this happens only during a full epoch. Okay? So that's the point of epoch. That's why we have slots and epochs. Good. So each validator votes exactly once per epoch. Nice. Now, let's look more in detail at the votes. Like, voting what exactly? And I said, what is the vote? The vote is what is you are telling the rest of the network, what is your view of the blockchain. You're saying, this is the blockchain. That's your vote. Now, in an ideal case, that's not the truth, it's really the ideal case, in which there is no potential disagreement, then this is very easy. I imagine there is really only one blockchain and every node sees exactly the same thing. They all believe that this is what happened in history. Because again, all nodes have their own view. They have their own view of history because they were online and they've seen certain things. Okay? So let's say that all the nodes have seen exactly the same thing, that is this history. That you have block 0, block 1, block 2, block 3. Over time, every 12 seconds, very nice. So proposer 0 proposes block 0. Proposer 1 comes in with the block 1 and says, this is the new block, and I'm building on block 0. This was the previous block, and now I have a new block, block 1. Then proposer 2, the same. Block 2 building on 1, 3 on 2. Easy. So if you are the block proposer 7 at the slot 7, what you will do, you just build on 6. And if you are not a block proposer, but an attester, and you need to vote, there is nothing to There's really nothing to choose. There is only one chain. So you're voting for this chain. Now, the truth, the reality is different, because at slot 7, what can happen is that you have seen something really different, like very different from the previous case. So let's say we're at slot 7, and you can see both from the view of the block proposer and the attester. If you're block proposer at the slot 7, you have seen in history, you have seen weird things happening. So this is what you have seen. This is your history. And you care about your history because you cannot blindly trust nobody, because open participation, decentralized trust. So you have to care about and trust what you've seen. Okay, only that, and believe in the protocol. The protocol works, so it's a good belief. But anyway, this is what you have seen. You have seen a slot 0, B0. Then you have seen forks, because you have seen a block 1 building on 0. But then, after some time, you have seen a block 2 again building on 0. Weird. So you have a fork here. This is what we call fork, because there are two versions of the blockchain at this point. There is one blockchain here and then one blockchain here, because really blockchain is append only list of transactions. It's sequential, one after the other. You don't want forks, like there is one history, because everyone will then run the same history and know that they have the same state. And that's what users care about, this database, this valuable information for Ethereum users. Okay, so block 7, I've seen this history, and to make things worse, there was another fork here. So block 7 has seen this happening, and they have to they have to add the next block or propose the next block. When you propose the next block, B7, not only you propose a block, well, yes, you only propose a block, but inside the block, it said, I'm building on the previous block. Like, what is the previous block? So you have a choice here. You're building on B6 or B5 or B4. How do you do that? What is the rule? That's the fork choice rule. So this we'll see. Because you have to choose a fork. You have this chain, you have this fork, and you have to choose where you want to build. This is true also for attesters, because the attesters, like all the other nodes, they have to vote on what is the right chain. So the attesters will also have a view of the forks. Let's say it's this, but different attesters can have different views. They have seen something else, maybe. Their history will look a little bit different of the blocks that they've seen. But in any case, they will need to make a vote and say, this, according to me, is the tip of the chain. This is the view. This is the right chain we need to keep building on. You will need to apply a fork choice rule to vote. So that's the vote. Say, this is the right chain. Okay, so how does this fork choice rule actually work? There's this algorithm, is LMD Ghost. Last message driven, greediest, heaviest observed, sub-tree. So we care about sub-trees, forks. These are trees, not forks. Because you have a root block, and then you have leaves that are the tips, and then the tree with the different forks. All right, so how does it work? As I said, you need a fork choice rule, and what is happening over time, every slot, validators, or precisely 1 divided by 32 of the validators, each slot, they vote on what they see as the right chain tip. Every validator in a slot potentially has a different view of this tree, because they've seen different blocks, different things. They might have skipped something for whatever reason, so they might have different views. What they do, they vote. And with these numbers here, 20, 15, 10, 25, we put the votes. Now, the votes, as I said, they're also propagated. These attestations are propagated, aggregated. so that all the other nodes also see the attestations and keep track of who voted for what. So over time, validators, block proposers, and attesters have not only a view of the forks of the subtrees, but also keep track of how many attestations were given to the different blocks when they were the chain tip, basically. So there are these numbers. These are the numbers of attestations for every block in the different forks. Then what is the rule? Simple. Like really, you just need the attestations. And what the proposers do to decide which block they want to build on, in this case, there was these three choices. Block proposer 7 decides to build not on block 6, as these three blocks, but on block 4, which is a shorter subtree. Why? Because they apply LMD Ghost. What does LMD Ghost do? You count the attestation and you count the contributions of all the blocks in the subtrees. So they propagate. You can imagine these attestations propagating towards the root. So you have 25 and 20. You get 45. You sum, you get 45. This 45, you sum to 15, and you get 60. So 25. Basically, you assign weights to branches. So this is how it works. And the weight of this branch is the count of the attestation, not only of these blocks, but also all the descendants of the block. Okay? So 25 plus 20, 45, plus 15, 60. So this is the weight of this branch is 60. Now we apply the weights also to these branches. You have 10, so this branch is 10. And then you another 10 attestations, so this branch becomes 20. You sum another 20, and this branch becomes 40. Okay? So now you not only have the attestations for every branch, but the weights for every branch. So attestations for blocks, or slots to be precise, and weights for branches. Now, how do you decide then what is the right blockchain? You start from the root and you see what is the heaviest subtree. So you check the weights of every branch. You start from here and you see this branch weighs 60, this branch 40, 60 heavier than 40. Go here. B0, B2. And now you compare 25 versus 20. 25 is heavier, so you go here. B0, B2, B4. You reach the leaf of the subtree, you are done. You build on B4. And that's how LMD Ghost works from the point of view of the block proposer, but it's the same for the attesters. You will count the attestation, you build the heaviest subtree, and you vote for the chain of the tip. Nice. Okay, there is a concept here that I want to mention. There is the concept of block reorgs. So, again, you as a validator, let's say you're block proposer times 7, you have this view, and you've seen these weird things happening with the forks, and basically, this is a plot, a diagram in time. So, you at time 0, at some point you have seen this block 0. Then at some point, here in time, you have seen this block 1. So you thought this was the right chain. At this point, there was nothing else in this example. So there was really no way to vote for anything else. Like LMD Ghost was telling you, yeah, B1. And you thought this is the chain. But then, after some time, for sure here, we have seen that this is the right blockchain. So this block is like it never happened, because it will never be part, well, in this example, it's not part of the history of the blockchain at this point. So it never had an effect on the state. Doesn't have an effect on the state. To get to the right state, you have to execute this chain. What I want to say is that it's not like you see a block, You wait 12 seconds and it's over and you say, okay, that's the next block, I'm sure. No, because it can be reorged. It can be like it never happened. Because now the write history is B0, B2, B4, B7. B1 never happened. So you can't assume that the block is finalized after 12 seconds. Finalized meaning this idea and belief, or anyway assumption that the block happened and it will never be reverted, and you know that the transactions that are in this block in that order are forever history of the blockchain. You cannot assume that you have this finalization state after only 12 seconds. And again, this makes sense because you have to remember that every slot in 12 seconds, only 1 out of 32, 1 divided by 32 of the validators have voted on that slot. So it's a bit, dangerous. Like, you shouldn't. Like, let's wait for all the validators to vote. What I mean by this is that finality is based on epochs and not slots. LMD ghosts and the slots and this fork choice rule is for liveness, meaning that you know that every 12 seconds something will happen. There will be a new block, or anyway, everything is in order for having a new block, but finality is achieved at a slower time scale because you need to wait for all the validators to be able to vote. And for that you need epochs. Now, how does that work? There's another algorithm. It's Casper FFG. It's a friendly finality gadget. Yeah, I think. Anyway, and it's a finality gadget, meaning that it's on top of LMD Ghost and it allows finality. So how does that work? There is something I didn't mention before when I said a tester's vote on what is the right blockchain, what is the right chain tip. We're saying, my view at this moment in time in this slot is that this is the tip. And by saying the chain tip, you also say what is the history because its block is pointing to the previous block. I say this is the right blockchain. But that's not the only thing that you do. You don't vote only. So you vote at your slot, one of the 32, but you don't talk only about the tip, like what is happening at this slot level, but you vote also at epoch level. So this longer time scale. And that's how we are starting to talk now about finality. So how does it work? If at least 2/3 of the validators agree on a link between a source and target checkpoint block, then you establish a supermajority link. So to talk about Casper FFG, we need to mention these definitions: checkpoint block and supermajority link. So every epoch will have a checkpoint block, and that's the first block, if it's a full block, if it's there in the slot. So normally the first block of an epoch. In this case, the block at S0, slot 0, you will have block 0, that's checkpoint block of epoch 0. And epoch 1, you will have slot 32 as the first field slot, the first block of epoch 1, that's the checkpoint block. Now, what your vote is, on top of what we discussed of LMD Ghost, you also say, as an attester, a validator, you say, I believe that the source checkpoint is, for instance, S0, and the target checkpoint is S32. Because that's what you've seen. That's your history. It's really the same concept. You have a certain view of what happened. But now we are not talking at slot level, but at epoch level. So we need the concept of, we only care about checkpoint blocks. It's one block per epoch. It's basically you're voting at epoch level, at that time scale. And yeah, you vote for a source and the target. And now the other concept is and that's your history. You've seen this source and this target. Now, the concept of supermajority link. What is supermajority link? It's a link that is established between a source checkpoint and a target checkpoint if there are at least 2/3 of the validators, 66% of the validators, that agree, that they are in agreement, they all vote the same thing, they all say, at least 66%, that the source checkpoint is S0 and the target checkpoint is S32. This is what I mean here by this 3%. I mean that by this time, because we are here in time, one slot passed in epoch 1, there are 3% of the validators, so 3% of the whole validators you have all in these epochs, but they don't vote all the same time, but only 1 out of 32. So let's say you have 3%. These validators here, they all agree on the same thing, that the source target is, that the source checkpoint is S0 and the target checkpoint is S32. So they all vote 3% for this supermajority, for this link. They want to create a supermajority link between S0 and S32. Now, actually, what is the rule? What should you vote for? And again, this is deterministic. It's not like there are margins for doing things wrong. You just follow the rules, execute the client, it will work. But what is the rule? The source checkpoint is the highest justified checkpoint. So we need the concept of justified. We'll see. And the target checkpoint is the latest checkpoint you have seen. Now, there is another concept to know, that the very, very first epoch, by default, is justified. So let's say really this is the beginning of Ethereum, the first epoch. This epoch will be justified. And you are at this point in time, during the beginning of epoch 1, and you are asked to vote between source checkpoint and target, to give a source checkpoint and target checkpoint. Well, everyone will agree the source checkpoint is the first block of epoch 0. Because epoch 0 is justified, and the rule is that source checkpoint is the highest justified checkpoint. There is only one justified checkpoint. This is by default the genesis, the first slot. So that's your justified checkpoint, and then source checkpoint. For the target checkpoint, you see what is the latest checkpoint that you've seen. The latest checkpoint you have seen at this point is slot 32. So easy. You make this vote. Source S0, target S32, and you accumulate 3%. Okay, now time goes on, right? So there is another slot. Slot 33. Everyone agrees in this example. Also the people, the validator S33 will say, yes, we vote on source checkpoint being S0, target checkpoint being S32. They agree with the previous majority of 3%, and now we have 6% of people, of validators, voting for this link between source checkpoint S0 and target checkpoint S32. Now, if by the end of this epoch, this percentage becomes more than 66%, then this link will become a supermajority link. And in this example, this is what is happening. So we finish this epoch, and now we have more than 66% of all the validators, because by the end of the epoch, all the validators were able to vote. More than 66% agree on this link, so this becomes a supermajority link. What happens when you have a supermajority link? So, if the link comes from, you have a link from we start from here. So you create a link from a justified checkpoint, then the target is justified. So links always come from justified checkpoint. Because that's the source is the highest justified checkpoint. By the way, you are justifying this epoch now because we created a supermajority link. So we went from justified, epoch 0, and E1 has no status. Now E1 is justified because we created a supermajority link from a justified epoch to now epoch 1 that also becomes justified because the target is justified. I said epoch 1, but I mean the checkpoint. So the target checkpoint now is justified. And the other rule is that if there is a supermajority link from a justified epoch, because the epoch 0 was justified, to the next, like really the following checkpoint, the one right after, then the previous checkpoint becomes finalized. So the source is finalized. Okay, so we went from here, justified, no status. Now, supermajority link, E0 becomes finalized, and E1 becomes justified. Okay, so now we can start a new round, because we are in epoch 2, and the validators in epoch 2, now they are asked again to vote on what they want to have as supermajority link. And now they will start saying that the source checkpoint is not E0, but E1. Because yes, E0 is justified and finalized, but the rule is that the source checkpoint is the highest justified checkpoint. So now the highest justified checkpoint is E1. So you're supposed to vote this. You're supposed to vote on E1 being the justified checkpoint, so the source, and E2, like S32 source checkpoint, and S64 being target checkpoint. So we're trying to build now this supermajority link. And again, this seems easy because I have only one version of the blockchain, or in this case, the chain of epochs. But this might not be the case, or you can have malicious nodes. So it depends on what is your view. But if this is your view and you're honest, you will clearly have this checkpoint is the source because it is justified, and this checkpoint as the target because it's the highest checkpoint that you have seen. So you want to make this checkpoint now justified. How do you do that? By creating a supermajority link. So that's what the validators are trying to do. But let's say that now, after slot 64, you don't have 3% as before, but only 2%. Why? Because maybe some validators vote something else, or maybe some validators are just offline. So it doesn't matter if you're offline or online for the supermajority. You want supermajority of all the validators. And if they're offline, of course, it's a problem because you don't know. Maybe all the honest nodes are offline. So you need to get them back. You don't want to just assume that that's not the case. So let's say you have only 2%, and then another slot, now only 4%. You finish, and now you have only 62% of validators in this epoch voting for this supermajority link between this source checkpoint and this target checkpoint. You didn't achieve 62%, meaning that this epoch is not justified because there is no supermajority link. And the rule is that the target becomes justified only if there is a supermajority link. Now there is a new epoch, and the vote, remember, the source checkpoint is always the highest justified checkpoint. So these validators at this point, they have to start from this source checkpoint, S32, and then the target checkpoint is S96. So this is the new supermajority link that we're trying to build. So it didn't work in this round, meaning that this stays justified, you didn't finalize, and this is nothing, and this is the new supermajority link. And what we're trying to do now is to finally finalize this and justify this. Well, actually, you cannot do that because finalization requires two justified epochs. So we keep going, we have 6% now, and then finally 66%. We created this supermajority link, and now you have a link from a justified checkpoint, a supermajority link, so the target is justified, this becomes justified, but the link is not from the previous checkpoint, but -2. So the source does not become finalized. As for finalization, in practice, you need 2 consecutive justified epochs. So because of this, we couldn't finalize this. But at least we have a more recent justified epochs, and now we can have another justified epoch here. So we have a supermajority link to the next epoch, and this finally becomes finalized. That's the idea. And yeah, you really care about finalization. You want to finalize a block. In this case, well, we are finalizing checkpoints, but when you finalize a checkpoint, let's say you finalize checkpoint S96, then all the previous blocks are also finalized. And what's the point of finalizing blocks? The point is that when a block is finalized, then you know that its effect on the state will never be reverted, or will not be reverted unless there is a massive cost for the attacker. And that's why we are talking about crypto economic security. There is an economic component. So in principle, you might have different conflicting finalized blocks, but only at a really, really high cost for the attacker. Basically, this would require 1/3 of the total staked ETH to be slashed. So we're talking about extremely high amount of value to be destroyed for conflicting finalized states. So in practice, you can say that when a block is finalized, so there is before a finalized checkpoint, then that will always be part of the history of Ethereum, part of the blockchain. Cool. Then let's talk about enforcing protocol rules. How do you make sure that validators vote according to the rules? They actually execute the client properly. They don't try to do malicious things like modifying the client to have different kinds of votes differently from what the other validators normally do. So as I said, the protocol includes penalties. So not only incentives for good behavior, but also penalties for bad behavior, like going against the protocol rules. And this typically requires really going out of your way to really try to attack the network. Like really potentially like modifying the client, modifying the code to vote differently. So what are the rules that you shouldn't break ever? And there's 2 things you shouldn't. There's one thing you shouldn't do in principle is equivocation. What is an equivocation? It's what happens when you contradict previously submitted attestations or block proposals. What does it mean? You first say one thing, like maybe you vote in one way, but then at some point you make a vote that is directly contradicting what you said before. So from the view of the protocol, this really looks like a way to attack the network. And it looks like an attack, and it must be treated as if it's an attack. Even if this happened by mistake, the protocol must be very strict, because it doesn't know. It really looks like an attack. If you want to attack the network, you do it that way. So you have to penalize badly, like harshly. And how is this done? By slashing the stake. So really a part of the ether that you deposited, we'll see more in detail, a part of it is destroyed. And the validator is banned, like out, like we don't want you. So you cannot participate you have to exit the group of consensus participating nodes. Of course, you can enter again at some point, but also part of the slash, part of your stake has been slashed and so on. But there are bad penalties if you have an equivocation. This is not only for votes, but also for blocks. So let's see more in detail. For LMD Ghost, when we are looking at the slot level, you will pay for an attestation equivocation, meaning that first you say that the right chain tip is a certain chain tip for this slot. Like you have to vote at your slot, and you said 2 votes that are contradicting each other. Like you really send 2 votes, and one says this is the chain tip, and then another vote says this other is the chain tip. You send 2 attestations. Don't do that. Then, proposal equivocation. If you propose different blocks for the same slot, like you're a block proposer, it's your time to propose a block. Instead of proposing a block, you propose 2 blocks, different blocks at the same slot. Don't do that. Proposal equivocation, so harshly penalized, because it can really look like an attack. Now, of course, it can happen by mistake, but the protocol, because maybe you're trying, you have know that maybe you're trying to have redundancy or backup nodes, and suddenly the second node goes online when the first node is not offline because your backup didn't work. Like there was a false alarm, and then suddenly you have 2 nodes that are voting at the same time, and they might at some point see different things, and then they will vote differently, and you were not malicious, but still the protocol does not know. It will slash you and ban you. So that's equivocation. And now that's equivocation from the point of view of LMD Ghost. We have equivocation also from the point of view of Casper FFG. Or anyway, contradicting votes, this I want to say. And there are 2 types of contradictive votes. There is the double vote and surround vote. Double vote here in red, when you have 2 votes at the same target height. So let's say we're in epoch 2. You are one of the validators here, whatever slot here, because you are voting at epoch level. And other validators have seen you voting. I've seen you sending 2 attestations that are directly contradicting each other. Like at some point you said that there is a supermajority, that this is the source and this is the target. But then you say that this epoch 1 is the source and this epoch 2 is the target. So you have sent 2 votes at the same target height. Don't do that. Double vote. And the other thing you shouldn't do is a surround vote. And you can see it easily by looking at the arrow. There is an overlap. There is an attestation from you. They're saying that this is the source and this is the target. But then also there was another vote that was saying this is the source and this is the target. And you can see that this is bad because these really look like epochs, reorgs. Don't do it. Okay, then let's talk more about incentives and penalties. Very important for consensus. So let's start from the incentives. We have economic incentives in terms of protocol issuance and transaction fees. Because remember I said priority fees go to the block proposer. So you want to incentivize nodes or entities to join the Ethereum network and do the work to participate in consensus. And you do that by issuing rewards. So the protocol rewards good behavior, issuing, like really generating new Ether, creating new Ether and distributing it to good validators. What does it mean to be good? It means to propose blocks. So when it's your turn, you have been selected randomly, propose block. And you get rewarded for sending correct and timely attestations. So you're rewarded to vote for voting, but not just voting, but voting right. What does it mean voting right? It means voting for what becomes indeed the right chain. But you also have to vote in time. You cannot vote too late, because then what's the point? Like if you just wait for everyone to vote and then you see what is the actual history and then you vote after everything already happened, it's useless, and why would you be rewarded? So correct and timely attestation. Also proposed blocks. In a sense, you can imagine correct blocks. Like what I want to say, yeah, of course they have to be correct, but they have to land in the right blockchain. Good. And what else? For participation in SIG committees. This is important for light clients. But we didn't have time to talk about it, but it's just see it as another job that validators need to do. Then, so validators earn from this protocol issuance, and we can see them as consensus layer rewards. This issuance for being a good validator, follows the rules, and is synchronized. But then there are also rewards from execution, because priority fees and MEV go to a block proposer. Anyway, there is value from execution that is going to the block proposer. This is another incentive to be a validator, because if you're a validator, you can be randomly selected as a block proposer, and they're also from priority fees and MEV. How does the issuance look like? How much Ether are we minting every year, generating every year to incentivize participation in the network? It depends on the number of validators. So the more validators enter the network, the more Ether we generate. But it is not linear, okay? It's a square root dependence. So the issued Ether increases per year. The issued Ether per year increases with the number of validators, but sublinearly. What does it mean? It means that if you actually calculate the yield, the issuance yield per year, this decreases with the number of validators. So if more validators join the network, every validator will have a return based on issuance for these incentives from the protocol to incentivize participation in the network. The issuance, this yield decreases with the number of validators. And this makes sense because, you don't want infinite amount of validators, and you don't want necessarily too many nodes, because otherwise you would need too much time to achieve consensus, and there are many considerations here. But the point here is that you need security, you need decentralization, and you need the crypto economic security that comes from having a big amount of validators. But, there is a limit. Cool. Then let's talk about the penalties. So we talked about incentives for good behavior. We also have penalties and slashing, being banned for bad behavior. So penalties, slashing is what happens if you do something really bad. It's the equivocation. That's like really, really bad. Don't do that because it really, really looks like an attack. If someone is trying to attack the network, they'll do something that looks really like, that's equivocation. So don't do that. But then you have penalties, and this is minor. These are what happens if there is a minor offense to the protocol. So it's not that bad. What is that? Pretty much being offline. So, if you're missed attestations are penalized. So it was your turn to vote, you don't vote, because you're offline. Then it counts as a missed attestation, and not only you don't get the rewards for voting, you're actually penalized. So basically, your staked balance, because remember you deposit 32 Ether to get the vote. That's your staked balance. You can increase or decrease with incentives and penalties. Your staked balance will decrease. That's the penalty. And it decreases at the same rate as what you would have earned with attestation rewards. So not only you don't get these rewards, but you're actually going down in staked balance because of these penalties, because you're offline. Same story for the missing committees. Now, if you're slashed, then it's much worse, much worse, because you will lose more Ether for sure. So there is an initial penalty. There is 1 divided by 32 effective balance. Let's say 1 Ether. And first of all, you get this 1 Ether slashed. Not nice. So burn. And one of your Ether is gone. Second, you are banned. Like, you are queued for exit. You have to go. You have to leave. And you will only, so we are not anymore an active validator. You don't get rewards. And you can only withdraw in 36 days. So after 36 days, you can get out, because you have to go out, you're banned. Then potentially you can come back. But you have to wait. And for this time, you are not getting rewards. And you have got already this 1 Ether gone. Now, on top of that, there is a potential correlation penalty. at 18 days. So you are slashed day 0. After 18 days, slash day 0, you lose 1 Ether. After 18 days, there is a correlation penalty. That is potentially more Ether that is removed from your stake, depending on the total stake from other validators, maybe, that were also slashed in the same period. What this is trying to achieve is that if you have many, many validators that are slashed at the same time, then not only you lose 1 Ether, but you lose even more. And why is that? Because if there are many, many validators slashed at the same time, suddenly it really looks like someone is trying to attack the network. Because you have a coordinated, apparently, seemingly coordinated amount of validators that all try to break the rules at the same time. Suspicious. So, the protocol adds this additional penalty. In practice, this is a way to really strongly disincentivize actual attacks. Okay, so there is that, and then there are attestation penalties until withdrawal. So you never lose only 1 Ether, because until withdrawal, 36 days, you're not active, you are missing attestations. So your stake will go down. Not nice. And then there is this other very important concept of inactivity leak. So we talked about finalization, talking about Casper. And basically to achieve finalization, finalization happens every epoch, but you need 2 consecutive epochs for checkpoint 2, or the block corresponding to for the checkpoint to be finalized. Now you want to have finalization every epoch, staggered, like 2 epochs back. But we have seen that you might skip finalization 1 round because maybe you didn't create a supermajority link, so the new epoch is not justified, and you have to go back from the previous source checkpoint to create a new supermajority link, justifying the next. So what happens if you have 4 epochs where you don't finalize? That's really not nice and not ideal. Shouldn't happen. You should finalize every epoch. If you have 4 epochs without finalization, you trigger this inactivity leak condition, like an emergency state, let's say. Why it's called inactivity leak? Because a simple way to look at this, like an actual reason for not finalizing, is that imagine 40% of the network of the validators is offline, like for long. They're sleeping. They're just out. There is nothing that the rest of the network can do to finalize. You need 66%, and you have only 60% of the network active. The rest is sleeping. You need to get out of this, and you need a deterministic, clear, surefire way to get out of this. Because eventually you want to finalize. You cannot just find the people, wake up. No. So you trigger this inactivity leak condition. And what is this? This means that the inactive validators, the ones that are sleeping, that are offline, their balance starts decreasing. Just goes away. And this happens when the inactivity leak is on. And not only it decreases quadratically. So it's bad. It gets really bad real soon for the offline validators. And, they either wake up or the staked balance goes down for 32 Ether to 31, 30, 29, goes down. At some point it reaches 16, and when it's 16, validators are automatically ejected. They're out. When they're out, they're not part anymore of the validator set. So suddenly, your 60% becomes 100%. Now, you didn't need to reach 100%. 66% is enough to finalize. When you finalize, you are out of the inactivity leak condition. So yeah, that's it. And yeah, another detail during inactivity leak, there are no attestation rewards. But what is important is the inactive validator balance decreases aggressively. Cool. Future work. And yeah, this, yeah, I didn't make it super well structured. It's just a bunch of interesting things, I would say. What is interesting to me about future work on Ethereum, you have probably seen the roadmap diagrams by Vitalik. There's also this very nice article on the roadmap by Mike Dom. So I'll post that. But yeah, let's. This is just a very small selection of the things I care about. I think are interesting in the future work. So let's talk about modularity. It's very, very important because at the fundamentals section, I talked about the world computer. I talked about decentralized state machine, a global state machine, one global state machine. Now, this global state machine and this concept of one network, the nodes, one chain, one database, the state, super important information for all the Ethereum users. This concept is for sure representatives of what was the original vision of Ethereum. Ethereum is old, and Ethereum is it was huge, revolutionary, it groundbreaking and everything. So and it changed over time, of course, because technology progresses and we understand what works or not, what decentralization matters, which state. Yeah. Anyway, the original vision was Ethereum as a world computer. Like this state was really the world state. Everything running on the world computer. And all nodes maintaining one chain, and one chain providing data integrity for one world state. So that was the vision, world computer. I'm not saying the world computer is gone. The vision still lives. It's still useful as an abstraction, as a concept. But we have a different implementation. You don't have one network, one chain, one state, but you have more networks specialized for different functions, more chains, and more states. Okay? Different users will be more interested in different states. All right. And we see what it means, modularity. But still, the Ethereum state is important. So all the networks in this modular world and all the states will rely on the same source of decentralized trust. So we go back to the first slide. And this is coming from Ethereum and Ethereum State. So yes, there are still a lot of people who actually care about the integrity of this state. They might not know, they might not look at it, but the integrity of the state is super important. And what ensures the integrity of the state? The Ethereum blockchain. And what ensures the Ethereum blockchain is safe and live, maintained and everything and secure? The network, the Ethereum nodes. So that's the source of everything. Cool. Modular stack. So a few more words on the modular stack, because this is not future, this is current work, like this very clearly what Ethereum is building. It's building for a rollup centric roadmap for this design in which you have more states at the execution layer, at the execution level. And who's maintaining these states? Well, different chains. They are the rollups. So Ethereum development efforts focus on optimizing it as a data availability and consensus layer for rollups. So you have this modular stack, DA, consensus, settlement, execution, different networks optimized for different features. And, at the end, the end users, one end user might care, like the state they actually care about is maybe only one of them, only one of a specific rollups. And the users enjoy cheaper and faster execution. So they like this state because it's cheaper to request write on this state. And because this state has the information they actually care about. They don't care about the world state, all the rest of the information. I care about a specific database. So it's specialized, it's more like closer to user, and it's cheaper and faster to execute. That's what the rollups are trying to achieve, and their integrity depends on the security provided by Ethereum as a data availability and consensus layer. Then you have settlement as a function with validated bridges to ensure that the integrity of the rollup states is secured by Ethereum. So you care about the state, but what is this additional value to the user I talked about at the beginning? Part of it, you want safety. So you want integrity. You don't want that the state changes randomly or that anyone is changing the state machine operation rules. You still care about decentralization and security. This is coming from Ethereum, and how is it coming from Ethereum? Thanks to settlement and validating bridges. That's how the rollups inherit security from data availability. So let's talk about, more precisely about what a rollup is. The rollup is defined by software that parses ordered data blobs and calculates the next state. So data blobs are posted on Ethereum by this software, by the rollups. Why would you do that? Because then you can inherit security from Ethereum. And now you can connect to the other resource, the data availability resource, or blobs. You're using Ethereum here for data availability only and ordering of the blobs, so consensus. Because you're not asking Ethereum to execute these blobs. So there's no execution gas needed here, only blob gas. Because execution happens at the rollup level. The rollup is the software that posts blobs on Ethereum. Or anyway, there are these blobs on Ethereum. There's just data. And Ethereum doesn't care about what is this data. The rollup cares. And the rollup state cares. So the rollup parses the ordered data blobs. Like the data blobs are ordered by Ethereum. The rollup looks at the data blobs and parses them in the sense that the rollup can interpret it, can know what is the meaning of this data that is posted on Ethereum. And then the software of the rollup software, calculates what is the next state. So they will have their own state transition function, so their own execution layer, might be an EVM, might be something else, looks at the blobs and execute the transaction, or anyway, execute the state transition function that goes from the state to the next state according to the order defined by the data blobs. So the rollups, how Ethereum provides security to the rollups. The rollups use Ethereum for DA, data availability plus consensus. Data availability means that the rollups post transaction data on Ethereum, and the network of Ethereum, the nodes, take care of, ensure that everyone had the chance to look at these blobs. Okay, they were propagated, they were made available in full to anyone who is interested. And to get this assurance and to post data and make it available, rollups will need to pay Ethereum. What's the price? Depends on the cost of blobs, blob gas, DA gas. Ethereum full nodes, meanwhile, they don't care about what is in these data blobs. Why they don't care? Because they don't need to execute data there. That data is not part of execution of Ethereum. You don't need to use the EVM to process the blobs, because those are transactions that are relevant to the state of the rollup. So on the execution layer, on these other states, each rollup has its own state. So you don't need, as a full node, you don't need to execute every transaction of the rollup. That doesn't make sense. You also don't need to keep a copy of the L2 state. As an Ethereum node, you have one job from the rollup point of view, to make the data available and to order the blobs. Very important. So that's the consensus. How do you order the blobs? You just order the blocks. And the blocks will have a list of transactions, and some of these transactions are carrying data blobs. And you cannot have more than 6 blobs in a block, because we said blob limit 6. But yeah, the ordering comes directly from the properties of Ethereum, that is a block ordering network. So part of these blocks will be blobs. Awesome. So yeah, there are some rollups that we can maybe call smart contract rollups, or I heard classic rollups. In contrast to sovereign rollups. Anyway, these smart contract rollups, in this case, the settlement layer is also this validating bridge is nothing else than a smart contract on Ethereum. So with smart contracts, you can do anything. You can make a validating bridge that ensures that there is a commitment to the execution layer state. So the L2 state, you don't store it in full on Ethereum because it's the L2 state. It's not the Ethereum state. But you have a smart contract on Ethereum that stores a commitment of the L2 state. And this is very important because you might want to bridge Ether from mainnet layer 1 to one of these rollups. Why? Because you really care about an application that is in this state here, and it's cheaper to operate there. Whatever you want to operate there, you want to move your Ether from here to here. Well, you want to be sure that at some point you will be able to withdraw. And to know that, you need to know that there is state integrity, and to do that, you want to have a commitment of the L2 state on Ethereum, because Ethereum is what you can fully trust. Okay, ongoing work is on interoperability and reducing costs for rollups. Interoperability means, you have many states, and maybe you care about one, like one application here, but maybe you care about many, and maybe you want to operate at the same time on different states, but these are different networks. So, it's not super easy, but we're working on that. Ethereum is working on that, how to make these state transitions or moving from one chain, one rollup to another rollup in a very smooth way. So this is what I mean by interoperability here. And other ongoing work is to reduce cost for rollups, because the cheaper it is for rollups to operate, the more rollups you can have, the more scalability you can have, more applications, more transactions, more value. And how do you get the cost cheaper for rollups? You have to reduce the cost of posting data, so the cost of posting blobs. You have to make this more scalable, this resource more available or cheaper. And that's coming with a list of upgrades that we can summarize with dank sharding. Good. Now, another important topic from future work is censorship resistance and inclusion lists, like an implementation or a way to achieve censorship resistance or improve censorship resistance. So this is obviously super important. We said it's one of the main values or features. And then we don't want just to build a decentralized state machine, but a decentralized state machine for which censorship resistance is extremely important, like no compromise. What does it mean for a network to be censorship resistant? You want to make it very, very costly for a builder, and I didn't talk about builders yet, so let's say for a proposer, to exclude a transaction from a block. As you remember, proposer monopoly, 12 slots, 12 seconds. You have all the power to say, no, I don't want to add this transaction. You can do that. You can just say, no, I will just not include it. Okay, the next proposer will include it. So, no big deal, right? Well, it depends. Now, the point is, you want to make it very, very costly. It must be a huge opportunity cost to just find a way for an entity to keep a transaction away from a block. That would be or to just avoid, not for one block, but for many blocks. Okay, that's censorship resistance. So how do we know if there is censorship resistance how do we know if there is censoring in the network? You look at the mempool, so you look at the pending transactions, and if you see that there are pending transactions in some time. And there is space in the blocks, like the blocks are not fully allocated. You have these 30 million gas and you're not using it. And there are pending transactions that you might just add and nobody's adding them. Then it really looks like censorship. Like it's not a coincidence, it's not a mistake. Somehow the network decided not to add those transactions. That would be network level censorship. So we don't want that. We want to ensure that all transactions eventually, or as soon as possible, will find a way to get in the blockchain. So how do we do that? Or how we might do that is a proposal or a research direction. Inclusion list. So when you submit a block, you don't only publish a block, you can publish also an inclusion list. You publish also an inclusion list at the same slot. So slot 10, submit a block, propose an inclusion list. An inclusion list is a list of transactions that must be included by the end of the next slot, by the end of the next slot. This is a very strict requirement. Like if this proposal passes and if you have this upgrade, this means that if the block does not include all the transactions in the inclusion list, if they were not included already before, of course, then the block is not valid. So it's really strongly enforced. They must be there. And if they're not there, then all the other nodes will say, what is this block? Come on. And they will not vote for it. They'll say, this block is not valid. The transactions are not there. So the nodes will check the block at slot 10 plus 1 and the block at slot 10 because, maybe the inclusion list transactions were also included before. Okay. Then other concept, single slot finality. Nice. So we talked about slots and epochs. I said we need to wait for the epochs, for an epoch. Like we achieve finality at epoch level, not at slot level. You cannot be that granular. Every 12 seconds finalize. Not happening. Why? Because we have so many validators. 1 million validators almost, I think. If not, 950,000. Huge. And remember that we have only 10,000 blocks, or that's the order of magnitude. There is some inefficiency here. Because why would you ask for 1 million votes when there are 10,000 entities? So, in any case, we have 1 million validators, too many. You cannot aggregate 1 million votes in 12 seconds. It just doesn't work. There's no time. You can do it if you ask everyone to running more powerful hardware, but no. Then we have other problems. So there are different proposals, and one proposal is to increase the 32 Ether cap via validator consolidation. So now we have that you have one vote with 32 Ether, and that's it. You want to vote, you have to create a new validator, more votes, more. And you get more voting power by having more validator. Fine, staking more ETH, and that's fine. But this is adding strain to the network because you have more votes that you need to aggregate. So not good because then this number is blowing up. The idea here is to allow validator consolidation. So let's say you have 10 validators, 32 Ether each. With the new proposal to increase the maximum effective balance, you will have only one validator with 320 Ether. Now you have only one vote, but this vote has a higher voting power. When I say one vote, one message. But you keep the voting power. It's 10 times more than someone with just 32 Ether effective balance. but at least you don't have all these huge amounts of messages that are all saying the same thing because you control 10 validators and they vote all in the same way. It's extremely inefficient, and it must go at some point. So this is a proposal. Another proposal is to put a cap to the number of validators, maybe with rotating participation. So instead of having 1 million validators, you ask to have rotating committees. Not super easy to do, a lot of nuance. I would suggest to read this, but that's a possibility. Anyway, once you find a way to have fewer validators per slot, to have fewer validators in total, then suddenly you can ask them to all vote every slot. And then you have 100% of the stake. Anyway, all the validators voting every slot, and then you can have single slot finality. Achieve finality at every slot. After 12 seconds, the slot is gone, finalized, history will never be reverted. Cool. I mean, never, but the cryptocurrency security. Right. Now, minimum viable issuance, another very important and interesting direction of research. The point here, we talked about incentives, right? We said we issue Ether to incentivize participation in the network. Now the question is, how much Ether you want to issue? Like, how much is enough? How much security do you need? What is the right level of issuance to incentivize exactly that amount of security, this number of validators, amount of staked ETH that you want to have security in the network? How much is enough? Not obvious. But the concept of minimum viable issuance is that you don't want to overpay for security. As a protocol, you don't want to issue too much Ether, because at some point you have diminishing returns in security, but you are diluting all Ether holders that are not staking by issuing more Ether. So that's a concept, minimum viable issuance. It's an important field of research. Another concept related is that we have an issuance curve. We have seen the issuance curve before. Issuance curve, like current reward curve here. Number of staked ETH. Here we had the number of validators, but it's the same. Same relation. Here the number of staked ETH. And this is the Ether in millions that is issued. And this is square root dependence. This is what we have today. Now, if we believe that this is overpaying for security, and the minimum viable issuance is actually at a lower level than what we're doing now, then we need to adjust this issuance curve and bring it down, because we're saying we are issuing too much ETH. Okay? So this is research on adjusting the issuance curve to a level that is closer to the optimal, that is minimum viable issuance. Not easy, but I strongly recommend to go through the links. Amazing, well written, very clear, good stuff. So yeah. And another concept is that we want to avoid, it's also related, is the idea to avoid that all Ether ends up being staked, not having like 100% of Ether being staked. Because most likely, what would happen is that all the staked Ether would actually be liquid staked Ether through the issuance of liquid stake tokens by liquid staking protocols. And these LSTs would replace Ether as money completely. And there is at least one part of the community that is strongly against that, because having LSTs replacing Ether as money would introduce counterparty risk and would make Ether less neutral, honestly, if governance of liquid staking protocol has extreme power and the protocol would become too big to fail. I would suggest to read here, and there are reasonable arguments. Of course, there are also pushback arguments. it's not an obvious topic, and that's why it's interesting. So, so we have talked about adjusting the issuance, then maybe a more extreme, or anyway even further, if you want to avoid 100% of the Ether to be staked, well, you can actually have a target staked ratio. So I say optimally for the security, the optimum of the security we need is having a certain staking ratio, a certain component of the supply that is staked. To target that staking ratio, let's say 25%, 40%, whatever it is, one thing that you can do to ensure that you don't go way above that is to introduce negative issuance. And this is what we're seeing in these plots. And again, strongly recommended. So in this gray line here, you see the issuance that is today. And you can have this kind of issuance here in which at some point it becomes negative. So if you stake at this level, above 40%, your stake balance actually goes down. And by putting proper parameters on this issuance curve that goes down and becomes negative, then you can target a specific staking ratio. Good. Then another important concept is the one of proposer-builder separation, and then another important field of research. So the idea here, and yeah, I briefly mentioned builders now, so let's make it clear. We want to separate the role of the block builder from the block proposer. The block proposer, we discussed in detail what it is, selected randomly, one validator is selected randomly, and you have the power to decide which transactions are in, which transactions are out, and what is the order. Now, what we didn't say explicitly is that this is a big power. And why? Because there is value to be extracted. Well, how to say? Depending on how you order the transactions and on transactions that you might want to include, because you have all the power, you decide what is inside. You can put your own transactions, you can exclude certain transactions. Depending on how you do this ordering, you can get value as a block proposer. You can get a profit on top of the normal issuance, on top of the priority fees of the transactions. The way you order, include, exclude transaction will unlock value for you. And that's what we call MEV, maximally extracted value. And we can talk also about realized MEV, because what you actually extract is not necessarily the maximum theoretical. Anyway, MEV. Now, you can do this job yourself as a block proposer. You look at the transactions, you decide what to do, you get the value. But this is not super easy for many reasons. So what you can actually do, you delegate this job to a block builder. And block builder is a specialized entity that will do this work for you. I will tell you, order the transactions this way. And in return, they also get part of the value. Let's put it this way. So they do this job for you, they get a cut, you get a cut. And that's the MEV, part of the MEV supply chain. Block builder, block proposer. Now, this is already happening. This separation of roles from builders off-chain to proposers on-chain. That's why I say out of protocol is happening out of protocol with MEV boost. So dedicated software to coordinate different actors on-chain, off-chain. Now the idea for research is to potentially enshrine, so put it in protocol, PBS, proposer builder separation. So these roles defined by the protocol will be aware of this separation of roles. And this is something that, makes sense because it's already happening. And, we might try to fight this separation of roles because we like the idea that all nodes are the same and there are no central or anyway special entities with more power or difficult to access because they're very sophisticated, they need big hardware. But this is probably happening anyway. It's going to happen anyway, and it might be, for instance, required for dank sharding. Specialized builders is probably where we are going anyway. So at this point, it just makes sense to enshrine and have this separation with the proposers and builders at protocol level. Of course, there are ways to do this properly, to maintain values of fairness, neutrality, accessibility, censorship resistance of Ethereum. So that's the difficult part. So you want to ensure that proposers, even if they don't order the transactions, because this is delegated to the builders, proposers will still be able to enforce censorship resistance mechanisms. Yeah, so that's a very important point. And interaction, again, I have a link, I will post. These are all super good. Another point is Verkle trees for light clients and statelessness. So you remember at the very beginning in the fundamentals, we discussed about one of the values of this general purpose decentralized state machine. One of the properties it must have is end user verifiability. How do you achieve end user verifiability? Like imagine you want every user to be sure that everything is okay and don't need to trust anyone. So because you care about the data integrity of the state. So how do you know that the state that you see is the right state, data integrity, nobody tampered with it, this is the information I care about? You can run a node, okay? And nodes are relatively low hardware requirement. You can ask to run a node, but you cannot ask every user to run a node because yes, they are low hardware requirement, but not that low. They don't run on your phone. Maybe. Okay, they don't run. Anyway, they're not that low. No, they don't run on your phone. You need proper bandwidth and so on. Anyway, cool. What I want to say, yeah, you cannot ask every user to run a node, like a full node. But what you can ask is to run a light client because it's light, lower hardware requirements. And these light clients will be able to verify blocks without storing the state. So much lower requirements. And that's what you want to achieve. Now, the problem is that it's not that easy to do this with the way we store state today. It's with Merkle trees. We want to make it more efficient, introducing Verkle trees that make the size of the witness much smaller, and the witness is what you need as a proof to verify the integrity of the state. And you will just see this in the block, then you're happy. To verify, you don't need to store the state, the full state. The state takes size, and you want to have light clients, stateless clients. So with replacing Merkle trees with Verkle trees would achieve that. And that's a step closer to all users being able to verify the state without trusting anyone. Amazing. And I wanted to end this with this slide because, when I first read this blog post from Vitalik, was incredibly enlightening. And I think it really was a very, very good look in the future. So this was December 2021. And the idea was that different designs would converge over time. We had Ethereum plus rollups 2021 and big blockchain like a chain with big blocks. Let's say a chain with high hardware requirements. And both approaches would eventually converge to the same state if they want to provide value. If they succeed and they actually make sense and they actually, provide value in a way that makes sense, that they actually use decentralized trust, they will end up in the same state. Centralized production, like big block builders, decentralized validations, and strong anti-censorship protection. That's where we're going, no matter where we started. And the big blockchains, the Solanas of the world, they need to work at anti-fraud, anti-censorship armor, and user verifiability. Ethereum Plus rollups today, they might either have one big rollup scaling and dominating, or have many rollups with good interoperability, cross-domain MEV ecosystem. In any case, what will happen is big block builders, decentralized validators with strong anti-censorship protection, light clients, and this will work, and this all will make sense at some point. So let's go. 3 paths towards the same destination. All roads lead to the end game of centralized block production, decentralized trustless block validation, censorship resistance. That's all. That's the Ethereum story. And I don't know how long it took. It was fun and an honor to talk about Ethereum. Cool. Until next time, guys, people. See ya.